All right, so this says a six-sided die is rolled. Find each probability. First decide if they're mutually exclusive or not. Keep in mind that test-wise, that part of that question will not be there. You've got to train yourself to ask yourself if they are mutually exclusive. So if it's a this or a that, if you see the word or, think, is it mutually exclusive or is it not? That's what you have to figure out, okay, before you even start. So number 1 says the probability that the number rolled is less than 3 or greater than 5. There's that or word, right? So you have to ask yourself, is it possible for something to be less than 3 and greater than 5? No, right? So these are mutually exclusive events, which means we're going to do the probability that it is less than 3 plus the probability that it is greater than 5. So how many numbers in 1, 2, 3, 4, 5, 6 are less than 3? 2, and it would be out of 6 because there are 6 numbers there, right? And how many numbers are there greater than 5? 1. So this is 3, 6, or 1/2. Number 2, the probability of rolling a number greater than 4 or even. So is it possible, again, we see the word or, so we want to check. Is it possible for something to be greater than 4 and even? Yes, this time it is, right? So I'm going to do the probability that it's less than 4 plus the probability that it's even minus the probability that it is both less than 4 and greater than 4, not less than 4. Greater than 4 and even. So what's the probability that's greater than 4? 2 out of 6, good. Probability that it's even? 3 out of 6. Probability that it is greater than 4 and even? 1 out of 6, that number 1, right? I mean, number 6 is the only one that can do it. So I'd get 5 minus 1, which is 4 out of 6, or 2/3. All right, now we've got a card is randomly selected from a standard deck of 52 cards. Find the probability of the given event. So we obviously want to look at our standard deck of cards. You want to know it well enough to answer these kinds of questions. Number 3 says selecting a 5 or a face card. Now this is just one event for the first one, right? So you're just figuring out, these are still just one event. If it's an or statement, selecting a 5 or a face card. Is it possible to get a 5 and a face card? No, so I'm going to do the probability that it's a 5 plus the probability that it's a face card. So what's the probability that I pick a 5? 4 out of 52. How about a face card? 12 out of 52. And then we add them together, 16 out of 52, which is 8 out of 26, or 4 out of 13. Questions on that one? Okay, then I go to 4, selecting a face card or a diamond. Again, the word or there. Is it possible to have a face card and a diamond at the same time? Yes, these are not mutually exclusive. So probability of a face card plus probability of a diamond minus the probability of a face card that is also a diamond. What's the probability of picking a face card? We just said it, right? 12 out of 52. A diamond, 13 out of 52. And a face card that's a diamond, 3 out of 52. So this is 25 minus 3, which is 22 out of 52, or 11 out of 26. Questions on that one? All right, number 5, select an ace or a 9. Is it possible to be both an ace and a 9? No, these are mutually exclusive, so it's probability of an ace plus the probability of a 9. What's probability you pull an ace? 4 out of 52, a 9, 4 out of 52. I get 8 out of 52. 2 out of 13, thank you. And the last one, a 10 or a diamond. Is it possible to be both a 10 and a diamond? Yes, these are not mutually exclusive. So I'm going to do probability that it's a 10 plus probability that it's a diamond minus probability that it's a 10 and a diamond. All right, probability that it's a 10, 4 out of 52, diamond, 13 out of 52, and 10 and a diamond, 1. 17 minus 1, 16 out of 52. 4 out of 13. Questions? Now we're going to talk about, we're still talking about probability, but now we're going to talk about independent. Yesterday we just talked about independent, which was ones that the first case does not impact the second one, right? So this, first of all, they have to be two things, so this has to be an and statement. And we're going to look at them as like with replacement and without replacement. Am I affecting my overall sample space after my first poll or my first round or my first event? Or am I not? And that's the difference between independent. So the complement of an event is one way that we can find these. And the complement consists of all the outcomes that are not in the event. So if I gave you a certain event in the beginning, right? Like if I said, here's a die, roll the dice, what's the probability that you're going to roll 5 and under? Okay? There's one way to figure that out, which is literally to count your 5 and unders. The other way is to find the complement to that, which means find what's not 5 and under and then subtract it from 1. So sometimes there are less things outside of your set than inside of your set. Does that make sense? There are less numbers that are bigger than 5 on a die than there are that are 5 or less than 5. Yes? And so one way to find them is to do the opposite and then subtract it from 1. That's called the complement. So the little a with the dash over it is read as a bar, and that is how you find the complement. The complement would be 1 minus whatever the probability of a is. So sometimes you will see it, and again, it's kind of like your choice how you find it, and then sometimes you will literally see a problem that says, here is a, find a bar, and that's what it means. So example 6 says, when 2 6-sided dice are rolled, find the probability of each event. So you can make this little diagram every time you have something that has 2 6-sided die, okay? The top is the first time you roll, the left side is the second time you roll, and then the squares are the sums of them. So if I roll a 1 and a 1, I get a 2. If I roll a 2 and a 1, I get a 3. A 3 and a 1, I get a 4. And it builds this pattern, right? Now, I could go back, which maybe I will. I'll go back and count it again because we just used this one to answer that last question. But, okay, if I look at this diagram and the first probability is that it's not 6, are there more numbers in this box that are not 6 or that are 6? That are not 6. So my first choice is to just go through and count all the ones that are not 6, put it over 36, and that's the answer. The other option is to count all the ones that are 6, 1, 2, 3, 4, 5, and say this is not what I want, right? This would be the complement to it. So 5 out of 36 is what I don't want, which means 1 minus 5 out of 36, or 36 over 36 minus 5 over 36, 31 over 36 is the complement to that, which is how I could also get this answer. So if there is more options of it not happening, you might choose to use the complement, which is what we just said. B says the sum is less than or equal to 9. So less than or equal to, again, I could look at my board and I could say all the numbers that are less than or equal to 9, which is here all the way up. Now, are there more numbers that are there or not there? Not there. So instead of taking the there, I can count the not there. 1, 2, 3, 4, 5, 6, and subtract that from 1. Does that make sense? So sometimes it's easier to do the opposite, and that's when the complement comes into play. You could still do it the way that you did it. This is just another way to do it. Questions on that one? Okay, independent or dependent. So we talked about this a little bit yesterday. 2 events are independent events if the occurrence of one does not affect the occurrence of the other. So we said this, an example of independent are ones like random generated number, rolling of the die, flipping of a coin, and then something that has replacement. Those would all be examples of independent actions. The first one does not impact the second one. The third one, a dependent event is the occurrence of one event does affect the occurrence of the other. This is pretty much just without replacement. So you have taken something out of your sample space and you did not put it back. That's the same slide. Ignore that one. All right, example 2. Tell whether the events are independent or dependent. So we're just identifying dependent or independent right now. A box contains yellow and brown dog treats. You randomly choose one dog treat from the box and you do not replace it. Then you randomly choose another dog treat. If your goal is to get a yellow the first time and a brown the second time, are these events independent or dependent? What'd you say? Are they independent or dependent? Dependent because of the words. Do not replace it. Example 3. A jar contains red and blue marbles. You randomly choose a marble from the jar, then replace it. Then you randomly choose another marble. Event A is the first marble you choose is red. B is it's blue. Independent or dependent? Independent. This time, you put it back. All right, conditional probability. So this is what happens when it's dependent. The probability that event B occurs given that A has occurred is called conditional probability. And it's written as probability of B equals probability of B slash A. So this is probability of B given A has already happened. And was successful. So when you do these, you are assuming whatever the first event is, you got. So if it was to pull a yellow dog treat the first time and then a brown the second time, when you go to find the brown, you assume the yellow was pulled. So you assume the first part is successful. Okay, probabilities of independent and dependent events. So independent events is what we talked about yesterday. Two things that you start with the same fresh sample space. And remember, we say if it's and, we multiply. If it's dependent, meaning that the first event affects the second event, we would take the probability of the first event and we would multiply it by the probability of the second event occurring, assuming the first has already happened. Again, these are both and statements. In order for something to be independent and dependent, you need them to be an and statement. You need something to have happened and a second event to occur. So exclusive and mutually exclusive are ors. Dependent and independent are ands. And conditional probability can be rewritten in different orders. If I just said that, I'll go back just a second. Okay. If I just said the probability of A and B is the probability of A times the probability of B given A has already occurred is true, then I can actually rearrange this if it wanted me to see what's the probability that B will occur if A has already occurred if you have the ending probability and the probability of A. So we basically just took this equation and solved it for the probability of B given A. So we can tweak those things. Sometimes it will say, if the probability that B and A both occur is this, and the probability that A occurs is this, what's the probability that B occurs given A? You can just solve it for the other missing thing. All right, so example 4 says you spin the spinner shown, which is divided into 8 equal parts. Find the probability that you get red on your first spin and blue on your second spin. So again, these are going to get grouped together with all the other word problems on your test. You want to be able to differentiate the difference between what we're doing before and now. First thing I should notice is get red on your first spin, and then the word and then blue on your second spin. So I know the and means I'm going to multiply. The question is, are these independent or dependent? So if I spin the spinner and I get something the first time and I go to spin it a second time, is my sample space changed? No, which means these are independent. So I want the probability that you get red times the probability you get blue. What's the probability you get red? How many spaces? 1, 2, 3 spaces are red out of how many total spaces? 8, right? There's 8 total spaces. How many spaces are blue? 1, 2, out of the 8, same 8 spaces. So now I can simplify this, make my life a little bit easier, multiply it, and my chances are 3 out of 32. So again, notice the word and is there, not or. Or would be a single spin. Easy stuff, right? Example 5 says, a bowl contains 36 green grapes and 14 purple grapes. You randomly choose a grape, eat it, and then randomly choose another grape. Find the probability that both events A and B will occur. A is the first grape is green. B is the second grape is green. So first of all, the word and is there. I know that I'm multiplying, and I know that I have to figure out if these are dependent or independent. So if you randomly choose a grape, eat it, and then randomly choose another grape, are these events independent or dependent? Dependent. We're assuming we're not eating this grape and then putting it back. That would be gross. Okay? You have eaten it, which means from the first round, I need the probability that the first grape is green. Then I need to multiply that times the probability that the first grape is, or the second grape is green, given that the other green grape is already gone. So if there are how many green grapes? 36 and 14 purple grapes. How many total are in this bowl? 50. So the probability of getting a green grape the first time is 36 out of 50. What's the probability of getting a green grape the second time if the first green grape is already gone? 35 out of 49. So both the sample space of what I want or both the entire sample space and the outcomes are different. So you can again reduce this, 18, 25. 7 goes in there, 5, 7. 90. Oh, I can even keep going. Well, I'll just keep going right now. 175. 5 goes in there. 18. Which I would have gotten by also saying 5 and a 25 is 5. Same thing. Okay. 18 over 35. Questions on that one? Okay, tell whether the situation is independent or dependent and then answer the question. I'm going to let you try it. Okay, so a drawer contains 12 white socks and 8 black socks. You randomly choose one sock. You do not replace it. Then you randomly choose another sock. What's the probability that both socks chosen are white? Dependent or independent? Dependent, because we didn't replace it, right? So I need the probability that I'm going to pull a white sock. Then I'm going to multiply it times the probability I'm going to pull a white sock, given one of the white socks is already gone. So what's the probability I'm going to pull the white sock? 12 out of 20. What's the probability that I'm going to pull a white sock given that I already got one? 11 out of 19. So I can reduce this. 3/5, 33 out of 95. Number 2 says, suppose you flip a coin twice. What's the probability you get tails on the first flip and tails on the second flip? Independent or dependent? Independent. We don't lose the side of a coin if we flip it, right? What's the probability so I need probability the first is tails times the probability the second is tails. So what's the probability you land on tails the first time? 1/2. How about second time? 1/2, which is 1/4. Questions on those? Okay. Okay, example 7 says the table shows the numbers of tropical cyclones that formed during the hurricane seasons from 1988 to 2004. Use the table to estimate A, the probability that a future tropical cyclone in the northern hemisphere is a hurricane, and B, the probability that a hurricane is in the northern hemisphere. So the first thing you want to do is actually kind of just use some common sense here instead of using the formulas that we've had, and see if I look at A, it says that a future tropical cyclone in the northern hemisphere is a hurricane. So there's 2 requirements here, and the first is that it's in the northern hemisphere. From that, I eliminate everything in the southern hemisphere. So I'm talking about just these storms. Then the second thing says it is a hurricane. So I'm being specific to just hurricanes. So all I have to do is take that 545 and put it over the total amount that's in the northern hemisphere. 199 plus 398 plus 545, which is 1142. With something like this that says estimate, it usually means give it a decimal, a rounded decimal. So if I did 545 divided by 1142, I get 0.477%. And so this is usually something like 0.48 or 48%. B says the probability that the hurricane is in the northern hemisphere. So now I'm starting with the first being just the hurricanes, then the ones that are in the northern hemisphere. So I want the 545 again, but this time I'm taking it out of just the hurricanes, 545 plus 215, which is 760. And then 545 divided by 760 is 0.717 or 0.72 or 72%. Okay, example 8 says you randomly select 2 cards from a standard deck of 52 cards. What's the probability that the first card is not a heart and the second card is a heart? If A, you replace it, B, you do not. You have this one, right? Yeah, okay. All right, so we're going to look at A. You replace the first card. What does that mean? This is an independent, okay? And it says first card, not a heart, so that we need the probability that it's not a heart, times the probability it is a heart. This is kind of where a complement might come into play. So it's easier probably to count the hearts than it is to count the not hearts because there's more of them, right? How many hearts are in your deck? 13 out of 52. So if I did 1 minus 13 out of 52, or 52 over 52 minus 13 over 52, are you with me? Yeah, 39 out of 52. That's how many are not hearts. 39 over 52. And then I would multiply. So this is 1/4, and this is 3/4, and I'd get 3/16. What happens if I don't replace the card? It's dependent. So the first one's still the same. Probability that's not a heart is still 39 out of 52, or 3/4. But what's the probability that it is a heart if I didn't pull a heart the first time? God bless you. So if I didn't pull a heart the first time, does my amount of hearts change? No, but a card is gone, yes? So my total sample space has changed. It becomes 51. Does that make sense? Yeah? Okay. So this, and then actually you can put this, and I'd get 13 over 68. Questions? All right, so your part 2, let me make sure I have it